Hello everyone, this is Dr. C. What I'd like to do in this pre-lecture is focus on the rate law. And there's three questions, but the main question is actually how do we figure out a rate law of a given reaction? Okay, so here's our reaction. Here is experimental data, 3 experiments that were run, changing concentration, seeing what impact that had on the rate. And we want to determine the rate law. Now, the easy part is we always know the rate law will have the general form rate is equal to the rate constant K times the concentration of each reactant, in this case hydrogen, H2, raised to some power, the concentration of NO, nitrogen monoxide, raised to some power. That's the easy part. We know it's going to have that form. We don't worry about the products because we are measuring initial rate, starting only with reactant, going to product. All right, so our goal when we say determine the rate law for a reaction, what we're really doing is figuring out what these exponents are. What are X and Y? All right, so the way we do this is we look at different experiments. We hold one reactant concentration constant. We change another and see how that change in concentration impacts the rate. So as an example, let's start with experiments 1 and 2. What you'll notice is that the NO concentration stays the same at 0.0375. So this change in rate that we observed between experiments 1 and 2 was not caused by NO. It could only have been caused, assuming we keep the temperature constant. Let me point that out. These are at the same temperature. Okay, temperature, if we raise the temperature, typically the rate will be faster, so we want to hold temperature constant. And we change the concentration of hydrogen, and the rate changes. Okay, so any change in rate is only due to the hydrogen concentration. So what we want to do, and I'll show you the long way for the first one, the shortcut for the second one, we want to take one rate law divided by the other. Now I like to take the larger rate divided by the smaller rate. So since we're comparing experiments 1 and 2, I'm going to take rate 1 in this case, which is larger, okay, note your rates over here, divided by rate 2, all right, larger rate divided by smaller rate. Usually our exponents are positive. And if you do that, taking the larger rate divided by the smaller rate, we're going to work with whole numbers. Typically the other way, if you take the smaller divided by larger, you can work the problem. It's just that you're going to have to deal with some fractions. All right, so I'm going to write the rate law for experiment 1. Okay, and I'm just going to put a subscript 1 to indicate experiment 1. Okay, so there's our rate law for the first experiment. I'm going to divide that by the rate law from the second experiment. Okay, so a subscript of 2 to indicate experiment 2. All right, that's all there is to it. So we're always taking one rate law from one experiment divided by a rate law from another experiment. Now, what we'll find, since we kept the temperature the same, we can cancel out our rate constant. The rate constant is a constant for a reaction at a given temperature. Okay? Now, what we'll also notice is that NO concentration is the same. So we're plugging in the same number, numerator, denominator. So we can cancel that out too. And that greatly simplifies our calculation here. Because all we need now are the rates from experiment 1 and 2, and the hydrogen concentrations from experiment 1 and 2. That's all we need. So, rate 1, look at your table. 5.4 times 10 to the negative, oh, sorry, I hit the mouse button as I was trying to write. I don't think I ever make it through one of these without hitting something by mistake. Okay, so I'm taking rate 1 divided by rate 2. Concentration from experiment 1 divided by concentration from experiment 2 for hydrogen. and those will be raised to some power. And mathematically, since each hydrogen concentration is raised to the same power, we can pull that outside the expression. All right, that's not so bad, huh? All right, now 5.4 divided by 1.8, that gives us a factor of 3. 0.015 divided by 0.005, also 3, raised to some power. So 3 raised to what power is equal to 3? The answer is 1. Okay? So this is first order with respect to hydrogen, right? We canceled out NO. We were only changing hydrogen. So our X up here is 1. We'll write that out later. All right? So first order is the most common. Okay, we'll also see second order, and we'll also see zero order. All right, so we will, and you can have negative orders, you can have fractional orders, but for our purposes, we're most likely going to see first, second, or zero order, and we'll talk about that later. All right, so we figured out the exponent for hydrogen. Now we need to do the exponent for nitrogen monoxide. So we need to find trials where hydrogen is held constant, nitrogen monoxide is changing. And I think you'll find that that's experiments 1 and 3. Okay, hydrogen is held constant at 0.015. Nitrogen monoxide is changed from 0.0375 to 0.0125. All right, so now once you get the hang of this, the shortcut is we're holding hydrogen constant. So we're going to eliminate that from the rate law. We know the rate constant is a constant at a given temperature. We're going to eliminate that. So the shortcut is just saying, for NO, all right, I'm going to take rate, the larger divided by the smaller, rate 1 divided by rate 3. Again, we're comparing experiments 1 and 3 because we're changing NO, we're holding hydrogen constant. So any change in rate is not due to hydrogen. So again, the shortcut is, I know hydrogen's constant, I'm not even going to write it. I know the rate constant is constant, I'm not even going to write it. So rate 1 divided by rate 3, the only thing left in that equation is NO, concentration from experiment 1, raised to, let's call it Y, and NO from experiment 3, raised to the Y. Okay, so essentially we've done what we did for hydrogen, we've just pre-simplified it. That's kind of nice. All right, so let's write in our numbers here, and I'm going to write over here to the side so I can keep my table up there. So rate 1 is 5.4 times 10 to the negative 6th molar per second. Rate 3 is 0.6 times 10 to the negative 6th molar per second. And my concentration of NO, 0.0375 from experiment 1. From experiment 3, 0.0125, raised to some power. Okay, remember, it's always the concentration that's raised to the exponent. That's what we're trying to figure out. And what you're going to find here is we're going to get 9 is equal to 3 to the x, 3 to the y, xy. It's all a variable. Okay? So 3 raised to what power is equal to 9? And the answer is 2. 3 squared is equal to 9. So there we go. We have the two orders. We'd say this reaction is first order with respect to hydrogen. It is second order with respect to nitrogen monoxide. All right. Now, you will notice sometimes in these tables, sometimes we double the concentration, sometimes we triple. We're going to design our experiment. We're going to choose pretty easy factors. Okay? Double would probably be the easiest, doubling the concentration, see how the rate changes. But as you see in this problem, I tripled the concentrations and looked at how the rate changed. Okay? So if I triple the concentration and the rate triples, that's first order. If I triple the concentration and the rate goes up 9-fold, that's a squared term. 3 squared is equal to 9. So we're almost done. We do need to write out the rate law. That's what the problem asked for. We have all the information we need. Rate is equal to a rate constant, concentration of hydrogen, in this case to the first power. We typically don't write the 1. It's understood that it's 1 if we don't write it. and then NO squared. Okay? There's our rate law. All right, we'll do more of this in class, but I hope you get a good handle on it. A lot of times students struggle with these rate law calculations. But again, make sure we have to hold one concentration constant, change another one, and see how that changes the rate. All right, next question. We have our rate law. What is the overall order of this reaction? Okay, don't forget that hydrogen is first order with respect to hydrogen, second order with respect to nitrogen monoxide, 1 plus 2, third order overall. Okay, you just add up your two exponents. That's all there is to it. All right, last question. So now that we know the rate law, we can figure out some other stuff. Okay, so let's say we run a fourth experiment and we have our two concentrations. What would the rate of the reaction be? So we're changing our concentrations of both reactants. What's the rate? Well, if you look at this rate law, I know my nitrogen concentration. I know my nitrogen monoxide concentration. I want to solve for rate, but there's something I don't know. And what is it that I don't know? The rate constant. So how are we going to get that? Yes, good thinking. Remember, the rate constant is a constant for a reaction at a given temperature. So we can use any of the data up here to figure out our rate constant, because we know the rate, we know the concentrations, get the rate constant. We run that fourth experiment at the same temperature, it's going to have the same rate constant. All right, so we have, let's just use experiment 1, but we can use experiments 2 or 3. So we have 0.0375 molar for NO, 0.015 molar for H2, 5.4 times 10 to the negative 6th molar per second. I'm just writing these down on a sheet of paper so I can scroll down and write that out. Okay, so again, my rate, and I just did it again. So using the data from experiment 1, so my rate from experiment 1 was 5.4 times 10 to the negative 6th molar per second. I'm going to solve for K. Hydrogen from experiment 1 was 0.015 molar. NO from experiment 1 was 0.0375 molar. Squared, don't forget that it's raised to the second power. And now we rearrange this equation and solve for K. So what we're going to end up with is 5.4 times 10 to the negative 6th molar per second divided by 0.015 molar divided by 0.0375 molar squared. Oops, that should be squared outside. That's equal to K. And let's see what we get here. My value of K comes out to be, well, you should get the same value of K, 0.256. All right, so we have the rate constant. Now, we'll talk more about units in class, but what you'll see is one of the molarities in the denominator will cancel with one in the numerator. We're going to be left with molarity squared in the denominator, also seconds in the denominator. So we're going to end up with this as our unit. Okay? And we're going to find, and we'll talk more about this, that this molarity term that you have in the denominator is one less than the overall order. Third order, we end up with a squared for our molarity term. One less than the overall order. Okay? So the units of the rate constant will depend on the order of the reaction. All right, we are almost done. I apologize. This was a little longer than I anticipated. We are almost done. Now that we know the rate constant, we can plug in any concentrations and solve for the new rate. So let's plug these in. We want to solve for the rate for experiment 4. Our rate constant is 0.256. Concentration of hydrogen, 0.020. And concentration of NO, 0.050 squared, molar squared. Okay, let's see what we get. And the rate that I come up with is a former, sorry, I paused for a second. A former student of mine just walked by and knocked on the window of my office. Okay, 1.28 times 10 to the negative fifth. And what would my units be? Well, remember, rate is pretty much always going to be the same, right? Change in concentration over change in time. Molarity per second in this case. There's our second in the denominator. And if you want to check here, this molarity squared term here will cancel there, leaving us molarity in the numerator. Change in concentration, change in time. All right, now let's just see if our answer makes sense. Remember that rate, I should remember it too, 1.28 times 10 to the negative fifth. So what were my concentrations of NO? And I apologize, there's not much room here. 0.05 and 0.02 molar. So let's compare those to, say, which one is closest? Trial 1. Okay. I increased the NO concentration compared to experiment 1. I increased the hydrogen concentration compared to experiment 1. My rate should be faster. Since these are positive orders, first order and second order, I increase the concentrations of both my reactants, the rate should go up. And it did. It went from 5.4 times 10 to the negative sixth to 1.28 times 10 to the negative fifth. Okay, my rate essentially doubled, a little more than doubled. Okay, all right, thanks for hanging with me. We'll do more rate law stuff in class. Really work to get a handle on these. There'll be a couple of problems in the pre-lecture. I might just do 2 because these problems take a while, but just 2 where it's going to ask you to solve for the rate law. Oh, there is one other thing I have to mention because you might see this in a pre-lecture quiz question. Zero order. Okay? Also called zeroth order, but zero order. What does that mean? And what zero order means, it'd be like raising a concentration to the zeroth power, which is just 1. So what that says is that that concentration has no impact on the rate. Changing that concentration, rate will not change. Okay, so if you see a reaction where you hold the one reactant constant, you change the other, and the rate doesn't change, the one that you changed would be zero order, the reactant that you change. You change its concentration, rate doesn't change, zero order. You don't really even need to do a calculation. If you just look at your table and see, oh, I changed this, I tripled this, or I changed it by some amount, and the rate stayed exactly the same, that's zero order with respect to that reactant. So watch out for that. You might see that depending on the problems. They are randomized. Some of you might get zero order, some of you might not. All right, see you in class. Take care.